Hi, thanks for joining me. Today I'm going to be going over problem 3 from week 6 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be going through today. We have S to be the set of positive integers which can be written in the form x squared plus y cubed, where x and y are positive integers. So any number where you can write it as a sum of a square number plus the sum of a positive cube, then that's going to be in that set S. We want to prove that for any natural number n, which is at least 3, there exists infinitely many positive integers m, such that this set here has cardinality n plus 1. So we're looking at S intersect then all the positive integers between m plus 1 and m plus n squared. So m plus 1, m plus 2, m plus 3, and so on all the way up to m plus n squared. So we're looking at S intersect that set, and that will be some set, and we're looking at the cardinality of that set, and we want to show it equals n plus 1. So we want to show that there are infinitely many values of m that we can choose, such that this guy here has cardinality n plus 1. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so to start the solution, we're going to consider a function f from the natural numbers to the natural numbers union 0, so the positive integers to the non-negative integers. And it's going to take an input m, so a positive integer m, and it's going to spit out this guy here, the cardinality of S intersect m plus 1, m plus 2, all the way up to m plus n squared. So essentially our problem is to prove that there are infinitely many values of m such that f of m equals n plus 1. The first thing we're going to do is consider two consecutive terms of these f, so f of m plus 1 minus f of m, like so, and just plugging in the definition of f into this guy here, so S intersect. So when we're looking at f of m plus 1, we're looking at this thing here and placing all the m's with m plus 1s, so we're going to get S intersect m plus 2, m plus 3, all the way up to m plus 1 plus n squared, like so. And then we're going to subtract off just f of m, which is exactly this guy here, so S intersect m plus 1, m plus 2, all the way up to m plus n squared, like so. But now we notice that we've got an m plus 2 here and an m plus 2 here, and they're going to kind of cancel. And just to make it clear why that's going to cancel is because if m plus 2 is an S, then this m plus 2, and when we intersect it with S, it's still going to be in the remaining set. So m plus 2 here is going to constitute 1 to the cardinality of this top guy. But then it's, if m plus 2 is an S here, then it's still an S here. So this is also going to constitute 1 to this cardinality here. So we've got a 1 minus 1, and that of course cancels to give us 0. Similarly, for m plus 3, it's in here and it's in here. So if m plus 3 is an S, and that's going to constitute 1 to the cardinality here and 1 to the cardinality here, and we get 1 minus 1. And say, m plus 4, which is in both these sets here, suppose m plus 4 is not in S, well then it's going to constitute 0 to the cardinality here and 0 to the cardinality here. So we're going to get 0 minus 0, and we're still left with 0. So the only terms we need to consider are the ones which are, say, in this guy and not in this guy, and the ones that are in this guy and not in this guy. So that's precisely S intersect m plus 1 plus n squared, like so, and subtract off S intersect m plus 1, like so, because this m plus 1 plus n squared is this guy here, because we notice that everything else, m plus 2 is here, m plus 3 is here, and so on all the way up to m plus n squared, which is there. So that's going to cancel, and then we've got S intersect m plus 1, because we see that this guy here isn't in this set here, but everything else is. M plus 2 is there, m plus 3 is there, and so on all the way up to m plus n squared. So we're left with f of m plus 1 minus f of m is equal to this guy minus this guy, but we notice that this thing here and this thing here, they're both sets with just one element in. So then when we take the intersection of this with another set, what we're left with will be a set either with 0 elements in or 1 element in. So if m plus 1 plus n squared is in S, then this guy here, when we evaluate it, will just be the set with m plus 1 plus n squared in it. Or if m plus 1 plus n squared is not in S, then this will just be the empty set. So when we take the cardinality of it, it'll either be 0 or 1. So this guy here is either 0 or 1. And exact same reason, this guy here is also either 0 or 1. So f of m plus 1 minus f of m is something which is 0 or 1 minus something else which is 0 or 1. So it can only take a few values, namely it can either be 1, 0 or minus 1. So it can be 1 if this is 1 and this is 0. It can be 0 if these two are the same, so both 1 or both 0. Or it can be minus 1 if this guy here is 0 and this guy here is 1. So we've shown that the difference between two terms is either 1, 0 or -1. So that kind of means if we, drew the graph of f of m against m, we kind of just be either staying the same at bits or jumping up or jumping down by 1. So it will look kind of like a, I don't know what's called, a heartbeat monitor, something like that. But it's not going to, do massive jumps or anything like that. So remember, we want to prove that there are infinitely many values of m such that f of m equals n plus 1. But now that we have this piece of information, it in fact suffices to prove that there are infinitely many, let's say, m1s, such that f of m1 is less than or equal to n plus 1, and then infinitely many m2s, such that f of m2 is bigger than or equal to n plus 1. So if we can prove both these things here, we'll be done. Because if there are infinitely many m1s which such that f of m plus 1 is less than or equal to n plus 1, and infinitely many m2s such that f of m2 is bigger than or equal to n plus 1, well then that means that we've kind of got to jump across this n plus 1 boundary infinitely many times, and because this guy here only increases or decreases by 1, and it's a function which maps to the integers, so that means if it's going to pass that line, it's going to have to hit the line n plus 1 at some point in between. Like so, kind of like the intermediate value theorem, I guess. So if we can prove that there are infinitely many m1 such that f of m1 is less than or equal to n plus 1, and also we can prove that there are infinitely many m2s such that f of m2 is bigger than or equal to n plus 1, we'll be done. Okay, so that's my next task, to prove these two guys here. Anyway, let me clean up the whiteboard and we'll continue. Okay, so let's prove the first part of our two-part proof, and that is we want to prove that there are infinitely many m such that f of m is less than or equal to n plus 1. So the proof to this, we're going to start off by considering the cardinality of this set here. So the cardinality of S intersects 1, 2, 3, all the way up to k, where k is just now some arbitrary positive integer. Now remember what S is. It's a set of elements which can be written as the sum of a square plus the sum of a positive cube. And the reason I say positive cube is because obviously if you cube a negative number, you'll end up with a negative number, but we're not interested in that, because remember in the statement of the problem we have S equals a set of x squared plus y cubed, where x and y are positive integers. So from here on I'll just say cube, when technically I should say positive cube. But anyway, so S is a set of elements which can be written as the sum of a square and a cube, and we're considering this guy here. So this is essentially the set of, so essentially will tell us the number of numbers in this set here, so the number of numbers up to k which can be written as the sum of a square and a cube. But notice if we do have some number in this set, let's call it t, then we can write t, because it's in S, as alpha squared plus beta cubed, where alpha and beta are positive integers. But obviously it must be that alpha squared is less than or equal to k, and beta cubed is also less than or equal to k. Because if, say, alpha squared was bigger than k, well then if we just look at this thing here, we'd have t is already bigger than k plus some positive thing, so t would certainly be strictly bigger than k, and so it wouldn't be in this set here, so it would kind of contradict that it is in that set there. So if t is in this set here, i.e. if t is constituting 1 to the cardinality of this guy here, it must be that, the square part, so the alpha squared, we must have alpha squared is less than or equal to k, and beta cubed is less than or equal to k, and of course this is the same as saying alpha is less than or equal to k to the half, and beta is less than or equal to k to the third. So any element in this set here, we know we can write as a sum of a square and a cube, but there are only at most k to the half choices for alpha, and k to the third choices for beta. So that means the cardinality of this set here is at most k to the half times k to the third, which of course is k to the 5 over 6. Okay, so let's just quickly go over that. We've shown that if we take any element in this kind of intersecting set, then it can be written in the form alpha squared plus beta cubed, but alpha is at most k to the half and beta is at most k to the third. So that means that the number of possible ways we could get t is at most k to the half times k to the third. Now notice that it is certainly at most, and we can probably actually make this inequality a bit better, but we won't have to for this problem. But we probably could make it a bit better, because notice if we set alpha equal to k to the half and beta equal to k to the third, well then this thing here is going to be k plus k, so that's 2k, and that's certainly not in this set here, because 2k is bigger than k. So this is probably a little bit crude, but we could probably do a bit better, but we don't need to for this video. We have that this thing here, for any arbitrary positive integer k, is at most k to the 5 over 6. Now remember, we want to prove that there are infinitely many m such that f of m is at most n plus 1. The way we're going to do that is by considering kind of a weighted mean. So 1 over n times the sum from r equals 1 to n of f of r of n squared, like so. So we're going to show that there are infinitely many values of r, such that this guy here, f of rn squared, equals 0. And the way we're going to do that is by taking the weighted mean of all the frn squareds and show that that tends to 0 as we take capital N to infinity. So we have 1 over n times the sum from r equals 1 to n of f of rn squared. Well, let's just use our definition of f. This is just equal to 1 over n times the sum from r equals 1 to n of the cardinality of s intersect. Well, remember this is from rn squared plus 1, rn squared plus 2, all the way up to rn squared plus n squared. But of course that is just r plus 1 n squared. Like so. So this guy here is simply 1 over n times the sum from r equals 1 to n of s intersect, and then the set of positive integers between rn squared plus 1 and r plus 1 n squared. But notice, if we take, if we go from say r equals 1 to r equals 2, so when we do r equals 1, we'll get n squared plus 1, n squared plus 2, all the way up to 2n squared. But then when we plug in r equals 2, we're going to get 2n squared plus 1, which is kind of the next element across. So when we jump from one r value to the next, we're kind of going to, take off from where we left off. So when r equals, say, 3, we'll end up with a 4n squared there. But then when we move to r equals 4, we're going to get the 4n squared plus 1 here, 4n squared plus 2 here, and so on. So all in all, this kind of, where we finish off is where we're going to start off from the next kind of r value. So this is just equal to 1 over n times the cardinality of s intersect. Now plug in r equals 1, so we're going to get n squared plus 1, n squared plus 2, and so on, all the way up to this final value of r. So when r equals n, and the last term there will just be n plus 1 times n squared, like so. So this thing here is just equal to 1 over n times this guy here. But now we can use a thing that we proved, just plugging in k equals capital N plus 1 times little n squared, to get that this guy here is less than or equal to 1 over n, is from this guy here, times this guy here, so n plus 1 times n squared raised to the 5 over 6, like so. So we get the thing that we wanted to show, or 1 over n times the sum from r equals 1 to n of frn squared is bounded from above by this guy here. But then the next thing we're going to do is take capital N to infinity, and notice that, little n is just a constant, we can ignore that. But we've got an n plus 1 on the top, but that's only raised to the 5/6 power. But on the bottom we've got an n which is kind of raised to the 1 power, and 1 of course is bigger than 5 over 6, and they're both linear terms. So that means the bottom will kind of dominate, and this thing here will tend to 0 as n tends to infinity. So that of course means that this thing here, because of course this guy here is bigger than or equal to 0, because f is a non-negative function. So that means, kind of by a sandwiching theorem, this thing here will tend to 0 as n tends to infinity. But for this guy here to tend to 0, remember f takes non-negative integer values. For this guy here to tend to 0, it must be that frn squared is 0 for infinitely many r. Because if it was only 0 for finitely many r, well then that means that after some point, everything's going to be, each of the f's is going to be at least 1. So there's no way that this, this weighted sum can tend to 0. So we've proved that there are infinitely many r such that f of r times n squared equals 0. And that of course means there exists infinitely many m such that f of m equals 0. So whichever r's give frn squared equals 0, just do rn squared and plug that as, let that be equal to the different values of m. And we've shown that there are infinitely many values of m such that f of m equals 0. So of course that proves that there are infinitely many values of m such that f of m is less than or equal to n plus 1, because 0 is certainly less than or equal to n plus 1. So that's the first part of this two-part proof proven. Let's move on to the second part. Okay, so for the second part of this proof, we want to prove that there are infinitely many values of m such that f of m is at least n plus 1. And this is thankfully a little bit easier. What we're going to do is just let m be any power of 6. So we're going to say m equals k to the power of 6. And I claim that this works, so that f of m will be at least n plus 1. And obviously there are infinitely many powers of 6. So that will prove this claim and also solve our problem for us. Let's prove that f of m is bigger than or equal to n plus 1. And the way we're going to do that is by noticing the S intersect m plus 1, m plus 2, and so on, all the way up to m plus n squared, this guy here, this thing here is going to be like, I don't know if there's a name for this, but this thing I'm about to write down is going to be a subset of this guy here. And the thing I'm going to write down is simply m plus 2 cubed union m plus 1 squared, m plus 2 squared, and so on, all the way up to m plus n squared, like so. So I claim that this guy here is a subset of this guy here. I guess one thing to note is this thing here has cardinality n plus 1. Because, well, there are n elements here, one corresponding to each square up to n, and there's one element here, m plus 2 cubed. And notice firstly that n is at least 3. So that means that n squared is at least 9, so that's going to kind of be, you know, this m plus 2 cubed will kind of fall after this m plus 2 squared term. But notice that 2 cubed is not a perfect square, so it won't appear in this right hand side here. But anyway, each of these guys here I claim is in S intersect m plus 1, m plus 2, all the way up to m plus n squared. Well, clearly, all of these guys here are in this set, certainly, because they're all between m plus 1 and m plus n squared. But also they're all in S, and I claim that's true, and I claim that they all can be written as the sum of a square and a cube. And it's very clear for this guy here, because 2 cubed, well, 2 cubed is obviously going to be the cube, and because m is a power of 6, it's certainly a square number. It's k cubed all squared, so this guy here is certainly a square plus a cube. And then everything here, clearly the thing we got on the right, the 1 squared, the 2 squared, and so on, all the way up to n squared, that's going to be my square, and then m is going to be my cube, and it's true that m is a cube because it's a power of 6. K to the power of 6 is just k squared all cubed. So each of these guys here is also the sum of a cube plus the sum of a square. So we've got n plus 1 elements, which are the sum of cubes and sum of squares, and they appear in this set here. So if we look at the cardinality of each of these guys here, like so, this guy here, this subset thing, now changes to an inequality. We get this thing, the cardinality of this thing here is bigger than or equal to the cardinality of that guy there, and that guy has cardinality n plus 1. So this thing here has cardinality at least n plus 1, and this thing here is precisely f of m. So f of m has cardinality at least, f of m is just bigger than or equal to n plus 1, and that proves our claim, because again, there are infinitely many powers of 6 that we can choose for m to be. Anyway, I hope that has all made sense. It's a pretty fun problem, which uses, you know, we don't know what the m's are that give f of m equals n plus 1. We just know that there are infinitely many of them. But the first thing we did was just show that the difference between two f of m's is, or f of m plus 1 minus f of m, the difference between that is either going to be minus 1, 0, 1, which kind of means it's just a function which jumps up or jumps down or stays the same. And because it's an integral value function, it only takes integer values, then for it to be equal to n plus 1 infinitely many times, it suffices to prove that it's above that line infinitely many times and below that line infinitely many times. So kind of like by an intermediate value theorem, it must hit that middle line, the n plus 1 line, infinitely many times. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.